Hello to all of you who are attending the Eastern Energy Expo 2020. I greatly appreciate you viewing my presentation today on combustion analysis and combustion troubleshooting. My name is Tyler Nelson. I am the Instrumentation Sales Manager for the Americas for the Sauermann Group. I come from over 25 years of experience combined between the contracting and the manufacturing side of the business. I proudly hold my Master HVACR license in the state of New Jersey and also am a certified NATE instructor. My contact phone number is on the beginning of this presentation, and I will have additional contact info, email, and such at the end as well. Sauermann Group, who are we? We come from over 40 years of experience in the design and manufacturing of instrumentation. We produce HVAC combustion analyzers, HVAC testing instruments, refrigeration manifolds, industrial emissions gas analyzers, and also IAQ monitors. We are an innovative global company, and we've assembled some of the brightest minds from both Europe and the United States. And our one main goal is always having you in mind. We like to produce and strive to produce products that meet and exceed your expectations, provide training that is fast and accurate, and service that is fast and accurate, I apologize, and training that is both comprehensive yet easy to understand. And again, we appreciate you taking your time to view this presentation. Agenda, what are we going to go over today? We're going to go over a bunch of different things. We're going to go over why perform a combustion test with an analyzer. We're going to go over why we're here. I know your parents have always told you why you're here. My explanation is going to be a little bit different, but I'm sure you're going to appreciate it as it relates to our industry. We're going to go over the combustion process. What is combustion, excess air, CO2, direct O2 versus CO2, carbon monoxide draft. I'm also going to sprinkle in some troubleshooting and some other components in here as well. The combustion fairy. Now, I want you to take a look at this nice, fine fellow here. He is not living in your furnace or boiler. So our little combustion fairy does not exist. And since he doesn't exist, that means that we need to measure. So I know this is a little bit creepy, but thank goodness he doesn't exist. So again, it's important that we take the initiative and perform combustion analysis. Why are we here? Revolution and evolution. The revolution side of this starts with the manufacturers. Manufacturers analyze their warranty claims, and over the previous years, they've come to notice that in Europe, the warranty claims are 3 to 4%, and in the United States, they are 30 to 40%. And they started to delve a little bit deeper and to try to find out why. And they've learned that over in Europe, combustion analysis is mandatory fare. It needs to be done twice per year, and a piece of equipment also has a 10-year life cycle. So it is a government mandate. And then they look at what's going on in the United States, and they have noticed that it's obviously not governmentally regulated. And they've looked at those patterns, and they've realized that through sheer performing of combustion analysis, they can actually significantly reduce their warranty claims, but also prolong the life expectancy and reputation of their equipment. So since they can't have a governmental mandate in the United States, what they've now done is they've decided to make it mandatory for you to do a combustion analysis. For most of the manufacturers now, and basically all are going to be following suit, but for most of them, in order for your customer to qualify for extended warranty, you need to upload a copy of the combustion analysis to the manufacturer for that customer to qualify. In addition to that, the municipalities in the different parts of the United States are starting to enforce this as well. They're starting to make it mandatory in different pockets of the country that you perform a combustion analysis and upload that information to the construction official for any new furnace, any new boiler, or any new water heater that you install. And if you don't do that, they cannot approve your permit, which means you cannot get your final payment. Because normally in the contracting world, final payment is given upon final inspection. So the revolution is on the side of the manufacturers, but also on the side of the municipalities as well. And the evolution now is on the side of the contractor, because now contractors cannot do what they've done in the past. They now need to perform combustion analysis, because in all aspects of the HVAC business, it's going to become mandatory that it be done. And it's in the manuals, like you see here, where it shows combustion measurements will be made at this point. They're putting this in the manuals because they not only do they want you to test, but they're also requiring you to test. And you could see it here as well. CO2 targets, O2 targets for high fire and low fire that I've highlighted here. So that manual that you keep in your truck and that you pull out because it's nice and thick and you need an additional knee pad, well, there is very important information in the bowels of that manual that actually state what your combustion parameters are supposed to be, and that is what the manufacturers want you to follow. Manufacturers want you to test. They are creating testing ports. Here and here, as you see, these are not base and treble knobs, everyone. These are testing ports for you to properly do a combustion test. Also here on this concentric package, you see the exact same ports here as well. And down here, you don't see any testing ports on this high efficiency furnace. However, if you don't see them, guess what? You can make them. All you need to do is just drill a little hole in these intake and exhaust pipes here, and then insert a tap screw when you're done, but you create your own test port to be able to do a combustion analysis. Venting. It would be remiss of me to talk about combustion analysis if we didn't discuss venting. And as you see here, our beloved PVC, yes, the product that we've all been using for years, otherwise known as polyvinyl chloride, is going away. So if those of you that are viewing this are not aware that it's going away in our industry for venting purposes, it's going away. PVC, in the way that we're using it for exhaust venting on high efficiency or condensing equipment, was never intended to be used this way. It was never designed for the temperature tolerances that we're putting it through. And given that, we are now having challenges with the way the PVC is performing. You're getting odd shapes like you see here in this little serpentine view of a piece of PVC. And we're also not following the specifications on the master glue that we're using to seam it together with its various joints. And we're leaving air pockets in here because we're not following those specifications either. So PVC as a means of exhaust venting is going away, and it's being replaced with polypropylene piping. And there are companies out there now that are producing polypropylene piping that is obviously made for these temperature tolerances that we're using them for, but also have proper gasketing material so that we no longer need to rely on glue and the cure times for those glues in the hopes that it cures in time before we have to actually put the system on. So very important to note. And when we talk about venting, we also need to talk about the issues with venting. So the manufacturers think it's wonderful that we're now doing combustion testing. It's great. However, they're also realizing as a byproduct of that we're also venting their appliances incorrectly. Now, I don't want you to look at this slide and joke and say to yourself, wow, this was done for efficiency. No, it was not. When you vent something this way, when you tie in your supply and exhaust air into the same conduit, you're creating a potentially dangerous and hazardous condition for all those that are occupying that space. And that is why predominantly now, 9 out of the 10 manufacturers that are putting on classes for their equipment are actually instructing you on how to vent it properly because of issues like this here. Combustion. Before we go over what combustion is, I want you to think about it from this paradigm. I want you to view combustion as you view your annual physical at your doctor. When you go to your annual physical, you're having your height checked, your weight checked, your blood pressure, they're doing other diagnostic checks, blood and the like, and they're trying to ascertain the state of your health. Now, they're not doing it just by looking at you. Just you come in the office and they say, oh, you look like you put on a few pounds, just do this and that, pay your copay and be off, you're good. They're not doing that. They're actually doing diagnostic checking checking the internal workings of your body to make sure that you're functioning properly, and they're comparing those to the benchmarks of health based on your age and those other factors. So when we do a combustion analysis, that's exactly what we're doing. We are essentially checking the state and welfare or the health of that appliance, whether it's a furnace, boiler, or water heater. And what we're trying to determine is if it is meeting those certain acceptable benchmarks of health, i.e. oxygen percentage being normal, CO2 percentage being normal, CO ppm being normal. So if we're not performing a combustion analysis, we can't just tell by looking at an appliance how healthy it is. We actually have to delve a little bit deeper and actually do an analysis. And when we do an analysis, and we talk about combustion, combustion is essentially a chemical process between three major things. It's between fuel, it's between oxygen, and it also is between spark or an ignition. And when you combine those three things together and you collide them together, they produce rapid oxidation. Because combustion is akin to football, like a collision sport. You collide these three things together and you produce something. Well, what you're producing is you're producing heat, energy, or light, or in this case, fire. And by doing so, you're also producing the release of that thermal energy. And when you do that, you have byproducts that are being created. You're creating CO2, NOx, water, carbon monoxide, fuel, and also oxygen, or in this case, unburned fuel, and also oxygen. And the goal of any combustion process is to retrieve the maximum energy from the burning of those fossil fuels in the most efficient way possible. And unless we are performing a combustion analysis and using a combustion analyzer, we don't know as to what levels and to what concentrations and what byproducts we're producing. You know, this tagline here is pretty apropos, but it hits home pretty good. The best test while the rest guess. And that is true to form. If you want to be the best at what you do in our industry, it is very important that you perform a combustion analysis and take this concept seriously. When we talk about combustion, we have three different types. The first is stoichiometric. Stoichiometric is otherwise known as perfect combustion. And it's a hypothetical, it's a lab condition, and it doesn't exist. And it does not exist for these two specific reasons. The first and most primary is that stoichiometric assumes that we have 100% oxygen for our combustion process. And for those of you that currently use a combustion analyzer, and even if you don't, you know that the oxygen in the air that we breathe is 20.9%. And that is one of the numbers that you see when you first turn on a combustion analyzer. Outside in fresh air, you'll see that it says 20.9%. So since stoichiometric assumes we have 100%, we're already at a 5-2 disadvantage. The other issue or other reason why we cannot have perfect combustion, and it's a secondary reason, but almost as important, is that we have thermal loss in any combustion process. And stoichiometric assumes that we don't have any thermal loss or heat loss. Since we do, again, we cannot have perfect combustion. So we're left with two other types of combustion. The second one being complete, or otherwise known as good combustion. And complete or good combustion is the best fuel-to-air mixture to efficiently burn all of the useful fuel while leaving none of the carbon and hydrogen compounds left unburned. So it's a proper mixture there to make sure that we're using all the useful fuel and, again, deriving as much efficiency from that appliance as we can. However, for those of us that are not using a combustion analyzer, we seem to hover in the incomplete combustion category. And that is the third type of combustion, incomplete. And that is where we are having or producing, or due to inadequate air supply, we're producing carbon monoxide in higher ppm or concentrations than what is allowable. We're producing smoke and soot and other unsafe byproducts of combustion, such as NOx and the like. And we're also lowering the efficiency of that appliance. So the industry or the manufacturers are having us or wanting us to migrate to the complete or good combustion. That is what we strive for. But if we're not doing the analysis, first of all, we have no idea where we're at. And second of all, chances are we are finding ourselves in the incomplete combustion category. What is perfect combustion? A quick explanation of it is you have 5 molecules of fuel, 5 molecules of air. You put them together and you have a perfect 100% efficient burn of the useful fuels, getting all the efficiency out of it that you can. And that doesn't exist because we both know that stoichiometric doesn't exist. Thus, our perfect combustion scenario does not exist. So since that's the case, what are we left with? Again, we're left with the other 2 types of combustion. When we talk about incomplete, the way that I want you to understand it is as in this way, is that, for example, we're going to assume that this is a methane molecule for fuel, for natural gas, right? And it's 1 part carbon and 4 parts hydrogen. And when this methane molecule enters into the combustion process, all the hydrogen is flung off of it. It's almost like your arms and your legs becoming detached from your torso. But in doing so, the saving grace for this carbon is that it wants to attract 2 oxygens because it wants to convert itself from being strictly as a carbon into CO2, otherwise known as carbon dioxide, hence the 2. And in doing so, though, there are other versions of this same carbon that are trying to do the same thing. And since we only have a limited amount of oxygen for the combustion process when we're talking about incomplete combustion, there are some versions of the carbon that are going to attract its 2 oxygens and produce CO2 in proper concentrations, but there are also versions of this carbon that are not. And if we're not producing CO2, we are producing carbon monoxide because we're only attracting 1 oxygen, and that is a problem. So we have incomplete combustion, as I talked about with carbon monoxide. What do we have in our flue? High levels of CO, as you see here, high levels of the unburned fuel, which is in this case is natural gas or methane. So what do we have? We have an inefficiency that we've created with the appliance, and we're also producing high temperatures and smoke. So knowing this now and what incomplete combustion looks like, we can now look to migrate ourselves over to complete. And what does that look like? And it's the same example. We're taking that carbon, or we're taking the methane molecule. We are basically firing off all the hydrogens off, like we're, again, shooting off our arms and legs. But now the game has changed. Now we're able to introduce more oxygen into the combustion process by, in this case, possibly adjusting fuel pressure or changing the orifice or whatever it might be. But we're bringing in more oxygen into this combustion process. And by doing so, we are increasing the statistical probability that we are attracting the 2 oxygens that we're looking for, and we're producing CO2 in the concentrations that we need. So if we look at our flue here, our byproducts of combustions have changed, and we're in a much better condition. We're producing CO2, we're producing water, producing heat, we're producing oxygen. Those are byproducts of combustion that we want. Those are going to keep us out of the woods, so to speak, and out of trouble. So that's why it's very important that we understand incomplete combustion and its correlation and gateway to getting us to complete or good combustion. And when we talk about combustion, as I just touched upon, we want to discuss excess air. And excess air, by definition, is basically, it is, or to describe it, is due to fluctuations in fuel flow and lack of perfect mixing between fuel and air in the combustion zone, excess air is required to achieve more complete combustion of the fuel. Without enough excess air, formation of unwanted byproducts of combustion are created. We're creating the carbon monoxide that I just went over, the soot, we're having fuel losses or appliance inefficiencies. With too much excess air, we're decreasing the combustion efficiency, we are wasting fuel, creating pulling of the flame, and things like that. So the goal with all of this is to strike a balance where we between too much air and not enough air, and it must be maintained. So the perfect fuel to air ratio that a combustion analysis can assist you in getting towards is what we're looking to go for. Because if we look at this curve here, this gray shaded area, or this graph, this gray shaded area, this is where the manufacturers want us to be. This is our 0 to 22% or 22 ppm of CO. This is our 3 to 9% oxygen, and this is our anywhere from 5 to 11% of CO2. So it's very, very important that we understand where we're at, because this is our air-rich side of the equation, and this is our fuel-rich side of this equation. We always want to be on the air-rich side. And I'll further explain that here, where we look at direct O2 versus CO2 measurements. By only measuring CO2 directly, you can have the same CO2 on both sides of both the excess air and excess fuel side. So if we look at this, CO2, as you see here, this is a bell curve. And you can have the same amount of CO2 on both sides, whether you're on the air-rich side or the fuel-rich side, okay? That is why we need to take into account oxygen. Because if we negate oxygen, we are negating what proper combustion is, because it begins and ends with oxygen. It's one of the most important, if not the most important factor when we discuss combustion. But if we look over here, okay, the CO2 up here is fine. Our oxygen level is right in this shaded area here. Our CO is right in that 0 to very negligible amount right here that we see. But if we go to the air-rich side, look at what happens to our CO. So if we negate what oxygen is, we just pay attention to CO2, look at how high our CO is over here. This is where those of you, if you've ever spiked your CO sensor by doing a combustion analysis, this is what's happened. Out of all the adjustments that you make to a system, your CO is going to shoot through the roof. And you see over here that we have very, very high levels of CO, much far beyond what the acceptable levels are. So when you talk about having a blue flame and you think you have a blue flame so everything's working properly, it doesn't exist, because we can have the same blue flame on the air-rich side as we can have on the fuel-rich side. So we need to do a combustion analysis to know what side of this equation we're on, and also how to get there by making the necessary adjustments. Combustion troubleshooting, CO safety. It's very important that we take a second here and talk about CO. In our industry, we have one of the highest rates of dementia and Alzheimer's of any other service industry out there. It is because of our consistent and constant exposure to carbon monoxide on a daily basis, and we're not even aware. It is my hope that everyone viewing this, it wears a personal CO monitor before they go about their daily task if they're a contractor. For those of you that do not have a personal CO monitor, you should get one. But if you don't, your combustion analyzer has an ambient CO function that a lot of you are not aware that it has. You can actually monitor the CO in the space that you're in and know what the level is at, and know the level of safety or the ensured safety of the conditions that you're in. And when we talk about CO, it comes down to a few different things. First of all, obviously it's occupant safety, but it also, we have to look at the safety of the equipment. It's a major identifier of how our combustion process is proceeding. Obviously, very high levels of CO, or you're going to have very low levels of oxygen, and those levels are going to be unstable. And when you have high levels of CO, you're creating a potentially hazardous condition. So it's important that with a combustion analyzer that we do two things with it. One is that we monitor the ambient CO in the space that we're in. Second of all is that we pay close attention to what the CO levels are on our analyzer screen when we're actually performing a combustion analysis. When we talk about combustion troubleshooting and we talk about CO safety, there are a couple of things that come to mind. First one I just touched upon, and that is the monitoring of the ambient CO. Second one is the manufacturer's acceptable levels. In that manual snippet that I showed you in the beginning, it's very, very important to know and to understand what the acceptable levels are for carbon monoxide on the piece of equipment that you're working on. And you need to adjust the system accordingly so that you meet those specifications, because you don't want to put yourself at risk. You don't want to put the occupants at risk, and you don't want to have inefficiencies in the appliance. Another one is to check the source of the CO. This is where a lot of us get tunnel vision. We assume that the source of the CO is only the piece of equipment that we are working on. That is not necessarily the case. You can have a vehicle that could be parked in a garage or in a bay that could be running, that could be basically producing CO and having it infiltrate the space that you're working in. You could have a homeowner or a business owner's appliance that is producing CO, stove, oven, whatever other appliance that is producing combustion in there. So it can come from a multitude of sources. You could also be producing it from the actual appliance that you're working on as well, but it can come from a multitude of sources. So it's very, very important that we have situational awareness when we look at all this. Another one is correct analyzer use. We want to make sure that we're following the protocol on how to use an analyzer. And at the fundamental level, that protocol is to start up that analyzer outside in fresh air with no probes or hoses attached. Okay. This way it can establish a baseline. And that baseline is going to be 0 CO2, 0 CO, and your 20.9% oxygen, because that is the percentage of oxygen in the air that we breathe, as we discussed earlier. Another thing you want to be cognizant of is to know your levels. Outside of knowing the manufacturer's levels, you want to know what the acceptable levels are for CO in an actual space. And I'm going to show you a slide here in a second that's going to give that to you. But you want to be cognizant of what those levels are. The last thing I want to touch upon here is liability. Any piece of equipment that you interact with and touch, you're liable for, which means if you're a service technician or an installer, that not only can the building occupants or the owners or whomever, not only can they pursue your company if something went south, so to speak, or some negligence was found, but they can also sue you personally. So it's very, very important that you take this seriously and that you have proper situational awareness, understand how to use the analyzer, understand what the levels are, and understand what your function is there, and understand what the conditions are in the space that you're in. And if you see high levels of CO, you know how you're going to proceed, you know what your action plan is, and you know how to take the necessary steps. When I talked about levels a second ago, here are two that I want you to really key off on. 9 ppm over a 24-hour in any living space, and 35 ppm, maximum allowable over an 8-hour exposure. And that is technically your working day space, wherever your office is. So those two numbers are, I want you to understand at the foundational level and keep those in the back of your mind as you go forward and you look at your analyzer and you're trying to understand and conceptualize the levels that you're seeing. Is measuring draft important? Absolutely it is. What is draft? Draft is a pressure measurement. It is the rate at which the byproducts of combustion are exiting the flue or the exhaust. And draft tells you a number of things. It tells you, first of all, how the combustion process is taking place and how properly it's being done, but it is also letting you know how the combustion byproducts are leaving the space. Because if the combustion byproducts are not exiting the flue or not exiting the space properly and being terminated outside, then you have byproducts of combustion that could potentially leach into a space, cause hazardous conditions, and obviously create issues with the appliance, which I'm going to go over. So measuring draft. When we talk about draft, we have two different types of systems. We have an atmospheric system and we have a condensing system. Both systems measure draft in inches of water column. For an atmospheric system, the measurement is -0.02 to -0.04 inches of water column. In a condensing system, it is +0.02 to +0.08 inches of water column. In both instances, that is basically akin to the little combustion fairy that I showed you in the beginning. It's akin to that little combustion fairy gently breathing on the back of your neck. And I know that sounds very creepy, but that is what it feels like. So given that, and given then that's all of that draft pressure that you have to work with, anything that can happen that can alter the path of that draft or alter the pressure of that draft leaving can create an issue. And when we talk about atmospheric and condensing, they both have their own host of challenges. When we talk about atmospheric, we're talking about makeup air. And makeup air is the room space air, or the air that the furnace or boiler is sitting in, that it is taking in for its combustion process. And things that can impact an atmospheric system are if somebody replaced the stack or the exhaust with an incorrect size piece of pipe, that can impact the velocity and the way that the flue gases are actually exiting or leaving. If you have a barometric damper that is hung up or misbehaving, that can create a problem as well, because those flue gases are not going to exit properly and backdraft down into the system itself. And one of the last things is that if a homeowner or business owner has changed the layout of the furnace or boiler room, and by that I mean if there was once a louvered door on there, because that's what the room called for to provide it with enough makeup air, and if someone has replaced that louvered door with a solid core door, you're not getting the same amount of airflow going to that system because that solid core door is blocking it, because there are no louvers to allow airflow in. Or if a furnace or boiler was sitting in a nice open space and that building owner or homeowner decided to create an enclosed space where they kind of enveloped that boiler or furnace in an actual room and didn't allow it to have enough combustion air, that can create an issue for an atmospheric system. When we talk about a condensing system, that has obviously its set of challenges as well. One of the simplest things to check is, do we have an issue with our induced draft motor? Induced draft motor is integral in making sure that the byproducts of combustion are helping to leave a condensing system. And if there's an issue with that induced draft motor, that's a problem. Do we have the byproducts of another combustion process going down into our fresh air intake and impacting how the combustion is taking place and impacting how the flue gases are leaving? Do we have cracks or seams or cracks in these seams of our PVC piping that we've been using up to this point? Because I know you're all going to use polypropylene now after I just went over it. But if we have cracks in the connections or in the seams of our PVC piping, that is preventing the flue gases from exiting properly. That's an issue. And anytime we have flue gases that do not exit a system properly, what happens is that those flue gases go down into the combustion zone, whether it's atmospheric or condensing. And when they do, they are starting to wear away and eat away at the actual combustion zone itself, because those byproducts of combustion are not meant to go be backdrafted down in. So when we do so, or when that's happening, we're producing NOx. And NOx is an acidic gas. It eats what it touches. And what happens is that NOx goes into that combustion zone and starts to wear it away and starts to degrade it. That's an issue. Also, when we talk about a condensing system, we need to talk about cross-contamination. Cross-contamination is something that most people are not aware of, are not aware that a combustion analyzer can check for. And it can. Because when you talk about a combustion analyzer, it has 7 tools. It does your combustion analysis, yes. It's an ambient CO monitor, which I just went over. It's an ambient temperature monitor. It measures draft. It measures efficiency. It measures pressure, cracked heat exchanger, and it also checks for cross-contamination. The way that you do it is you simply put your probe into the fresh air intake for a condensing system, as close to the breech as possible. So, for example, you put your probe into this fresh air intake and you take a reading of what the oxygen is. That oxygen should be that 20.9% because you're measuring the fresh air that is incoming into that system from the outdoors. And it's 20.9% oxygen in the air that we breathe outdoors. If you don't have 20.9 and it's 18.2, 16.4, or whatever, you have cross-contamination. You have the byproducts of another combustion process infiltrating your fresh air intake. whether it is the exhaust from the appliance that you're working on or installing, or whether it is the byproducts of combustion coming from a water heater, a clothes dryer, or a neighbor's appliance. It doesn't matter. You have cross-contamination and it needs to be fixed. So when anything that is lower than 20.9 is producing NOx. So the greater the distance from the 20.9 that you are, that is the higher the percentage of NOx that you are producing. And again, the greater chance of that eating away at the combustion zone. Let's talk about a little bit of combustion troubleshooting here. Scenarios where we have low oxygen or high carbon monoxide readings. We have, one of the issues could be insufficient combustion air. When we talk about an oil system, that's one of the things we want to adjust is the air band. And when we talk about also insufficient combustion air, we want to adjust gas pressure or fuel pressure. We want to make sure that we're using a proper size orifice and that we're not adjusting gas pressure too much where we skew how that gas is actually being delivered into the system itself and for combustion. So we want to check for proper combustion air. We have a burner that is overfiring. Again, one of the things that we want to check is fuel. Is the gas pressure too high? Is the system misbehaving? Is the orifice improperly sized? So we want to check that if we have a burner that is overfiring. Another issue that can create low oxygen or high carbon monoxide is low stack draft. And in this case, as I talked about when we discussed draft, we want to adjust or install a barometric controller or barometric damper that we want to check and evaluate, or install one to make sure that we have proper stack draft. Do we have a cracked heat exchanger that is letting more air into our combustion process and thus affecting the way that the byproducts of combustion are drafting or are leaving? And I'm going to go over a quick 30-second check at the end of the presentation to show you on a forced air system how to check for a cracked heat exchanger with a combustion analyzer. Last thing in here that we want to check if we have low stack draft is, do we have an improperly sized chimney or vent? Are we using the correct size piping for our termination? Did somebody change it prior to you getting there? One of the things we don't want to assume is that the technician that was there prior did everything perfectly. A lot of times that doesn't exist. Don't assume anything, because remember, the liability is large. The health and welfare of both yourself and the occupants ties back to you. So you want to make sure that you're checking to make sure that that flue pipe or that exhaust venting is the correct size. Another item for troubleshooting, unstable readings. In that case, we're talking about unstable oxygen and unstable carbon monoxide. One of the things that could be the cause of it is the changing of weather or atmospheric conditions. If that's the case, we want to check the draft and or the barometric control. One of the things you'll notice as you traverse your different job sites that you go to, you're going to open up a door to a room and it's going to feel like you've just entered an airlock or a vacuum or a suction zone. That is because of the air pressure in that space. Well, when we have those changes of the atmospheric conditions inside of a space, we have changes to our oxygen and changes to our carbon monoxide readings. Those things can be altered. So it's very, very important that we closely monitor what those conditions are when we talk about the actual pressure in a space. Cracked heat exchanger. Obviously, the simple thing to do is to check or replace it, but it goes beyond that. We want to do our check weather analyzer, which I'm going to go over, and we also want to perform our visual inspection as well. But a cracked heat exchanger can cause, obviously, unstable oxygen readings and very high or unstable carbon monoxide readings. Excess draft. Again, we want to adjust and check the barometric control to make sure that it is functioning properly. Loose ports and doors and missing gaskets. Those are things that are rudimentary. So when you first evaluate a system, those should be what are considered your usual suspects. You want to make sure that the people that touch the system before you put the doors back on properly, that the gaskets were put on properly, or they're not falling off, or they're not compromised and need to be replaced. Those are some simple things that before you would get into more involved problem shooting or troubleshooting, that you should take a look out for and to account for. Where to test? We have a host of different systems here. We have your solid boiler with the draft hood here. We want to check for all things for both draft and also combustion right in this spot here, right underneath that draft hood there. For a water heater, notice I have two things here. First, I want you to check for draft as we go up in here. So you put your probe and check for draft in here. And then I want you to verify your combustion parameters down in here as we angle down in towards the tank. So for water heaters, we got these two different spots we should be testing. For high efficiency boilers or instant water heaters, we have our ports right here. A lot of times you're going to have your concentric ports where you can do your draft and also your combustion analysis right here. So you have your different ports right here that you would insert your probes in accordingly, that you'll see on a job site. 80% furnaces, you can see here, right in here. We want to verify our draft and our efficiency and everything else right here. It's close roughly to the breech as we can, or 3 to 4 inches off of it, roughly. Some will have you go a little bit higher, but if you're within this sweet spot here, you're fine. When we talk about a 90% efficient furnace, obviously we want to measure our fresh air intake. We want to look at the quality of that fresh air intake. And then we want to take a test of our exhaust air as well. That's where we want to do our combustion test. That is where we want to evaluate the byproducts of our combustion is on our exhaust or our termination setup that we have. And make sure, obviously, that we don't have other things that are influencing both our fresh air intake and our exhaust when we talk about a high efficiency or a condensing type of a system. And last slide here is something I really want to touch upon is your atmospheric system. I talked about atmospheric before when I talked about the different types of systems and as it pertains to draft. However, as you see here, you have different burners here. In a perfect world, I want to have you test all these different burners here. Test all the different burners to verify our combustion, to verify our O2, our CO2, and our CO and our efficiency. And then we want to check in here to verify our draft, our temperature rise, and things of that nature. But again, when we talk about atmospheric, I would like it a perfect world, and not everything is perfect again, but you can test the different burners here. Very important. And then we have your different systems here with your vent piping. Here's your places where you test in here. And then for the oil furnace, again, verify and test our oxygen, CO, and CO2 right up here in the actual termination piping here. And that's where we want to test for an oil system. And again, these are just general guidelines. And for those of you that work on the commercial side of things and don't think you can test, you can. This nice gentleman here working out in the hot sun on a furnace or on a rooftop system, you see here, he is actually about to perform a combustion test. And look, here's our vent pipe inside of here, right? Here's where our probe is inserted, right there. So if you don't think you can test or combustion test for a commercial system, you can. I have just as many customers that work on the commercial side of the business as I have on the residential side. And a lot of the contractors I deal with work in both sides. So it's very important for you to know that for both residential and commercial systems that you can do a combustion test. Combustion efficiency, atmospheric versus condensing. Again, we have these two different types of systems and both behave a little bit differently when it comes to measuring combustion efficiency. When we talk about combustion efficiency, whether it's for atmospheric or condensing, we're talking about three major things. The first is fuel. The second one is carbon dioxide. And the third one is delta T. So when we turn on our analyzer outside in fresh air, which I just went over, when we turn it on outside in fresh air and we go to test, one of the things we want to make sure is that we're set up on the proper fuel type. Because if we're not, that's going to impact everything else that is going to follow suit. And why I say that is that when you select the proper fuel type, your CO2 readings are going to come up and be calculated correctly, because CO2 is a calculated value. It is calculated based on the oxygen percentage. Remember, I told you before, oxygen is king. So it's calculated based on the oxygen percentage, but it's also calculated based on the fuel type, or the coefficients that are assigned to the fuel. So if you have the proper fuel type selected, the calculation will be correct when you're actually having your CO2 number be calculated. And the last thing we talk about is delta T, or otherwise known as change in temperature. So in that delta T, when we talk about combustion efficiency, is a change from the ambient room, in this case, to the actual stock temperature. So when we look at this example, again, ambient room air, say we're in a furnace or boiler of the room, and say it's 70 degrees. That figure there, it gets subtracted from our stock temperature of 300 degrees, and then we have a delta T of 230, or change in temperature. These three things, your analyzer will take, calculate them, and it will produce your combustion efficiency, whether for an atmospheric, whether it's 78% or 88%, it doesn't matter, but it will take these three criteria and produce your combustion efficiency. Now, my industry, to a degree, has led some of you astray because of the fact that there are a lot of combustion analyzers out there that do not have a secondary type K thermocouple port that will enable you to take a secondary temperature. And that secondary temperature is a major player when we talk about a condensing system, because combustion efficiency for a condensing system is calculated a bit differently than it is done for an atmospheric system. So as I mentioned, my industry has led some of us astray, or some of you astray, by not giving you that secondary type K thermocouple port. You need that port, or you need a way to actually be able to account for a secondary temperature. And in this case, for you, when you're looking at combustion efficiency of a condensing system, that secondary temperature is the outdoor air. So that needs to be accounted for. If, for example, on the previous example here, we use the 70-degree ambient air instead of the 20-degree air that we see here, which is from our fresh air intake. If we use a 70-degree air, our delta T would be wrong, because if we look at what it is here, for combustion efficiency, our delta T is 80. That is subtracting the 100 from the 20. That gives us a delta T of 80. If we took the 70-degree ambient air and subtracted from the 100, that would have given us a delta T of 30, and that would be wrong. And thus, we would have the wrong combustion efficiency. And having such a high swing between those two numbers, in this case 50 degrees, between the 70 and the 20, having such a high swing can produce upwards of an 8 to 9% swing in combustion efficiency. Remember, you must take a reading of the outdoor air temperature in order to get a proper combustion efficiency of a condensing system. However, if for some reason you don't have a separate type K thermocouple port, one of the things that you can do is you can manually override, in most analyzers, at least in Sauermann's or my company's analyzers, you have the ability, or we give you the ability, to actually go in and manually input what that outdoor air temperature is. And this way, when you input that in there, you will now be able to produce the proper, or the correct, combustion efficiency number for that high efficiency, otherwise known as condensing appliance. So something very important. And when I perform this presentation around the country, and I do live speaking engagements when we're not immersed in the conditions we're in, I ask for a show of hands when going about combustion efficiency, who thinks they're doing it right. And most technicians will raise their hand and say, oh, I think I'm doing it right. Well, when I get done with this part of it, 9 out of the 10 of them will raise their hand again saying, nope, I was doing it wrong, because they were not aware they needed to take an accounting of that outdoor air temperature, because the analyzer that they were using didn't have that secondary port and didn't lead them down the path to wanting or needing to take that temperature. So it's very important that we account for that. Cracked heat exchanger tests. This is something that you would do on a forced air system. This is something very important. Now, it doesn't matter the experience level of the technician when it comes to this, because an analyzer can help the most inexperienced tech look very intelligent and can also help to bolster the most experienced tech's credibility as well. Because when you're an inexperienced tech and you're relying solely on visual inspection of a cracked heat exchanger, there's a pretty good statistical chance you might miss the visual inspection part in trying to find a crack. However, an experienced tech could miss it as well. So given that, you have a high level of variability there. Well, Combustion Analyzer kind of negates that or solves that variability quotient. Because with a Combustion Analyzer, you're able to check and test for a cracked heat exchanger in about 30 seconds. And the way that you do that is this. You're simply going to approach, whether it's an atmospheric or condensing system, it doesn't matter, as long as it's a forced air system. The system is going to be off. You're going to insert your probe into the stack, into the exhaust. You're going to turn the system on. The combustion process is going to begin. You're going to look at your oxygen levels once they stabilize. It's going to be anywhere from 3 to 6% or 3 to 9%, depending, but mostly between 3 and 6, somewhere in that range. But for our example today, we're going to say 4.8, as you see with my little highlighter here. Once the fan kicks on, you're going to continue to look at your analyzer. If that oxygen level starts to decline, if it goes to 5.6, 6.4, 7.2, there's your crack. And the reason why is combustion is a sealed process or protocol. And when the fan kicks on, if there's a crack in the heat exchanger, through the negative pressure and entering in through that crack, you are allowing additional oxygen that is not supposed to be in your sealed combustion process. So you're introducing more oxygen that's not supposed to be there. And by doing so, your oxygen level is starting to rise as that fan and that system continues to run. So whether it's 5.6, whether it's 12.4, either way, you have a crack. And the last time I checked, cracks don't get smaller with age. They get bigger with age. So depending on if your carbon monoxide levels are high or not, either way, that the remaining numbers in the oxygen percentage, but the remaining CO and CO2 numbers, that is going to set you on a direct path as far as what your recommendations are. Do you have a crack in the heat exchanger? Is it an issue with the rings on the heat exchanger? Whatever it is, as it relates to the heat exchanger, you can now develop a plan of action, and you can also fully ascertain how safe the conditions are for people to actually be there. But again, remember, the crack's not going to get smaller, it's only going to get bigger. And having said all of this, in giving you the technology insight or technological insight in how to perform this test with a combustion analyzer, that doesn't mean that I want you to negate or just throw away your technical ability and not look for the crack in the heat exchanger. You should still perform your visual inspection. Don't forget everything you've ever learned as a technician and say, oh, I attended this presentation on combustion analysis. I can now do this with my analyzer. I'm good to go. Don't do that. Always keep your skills fresh and current. Always stay engaged. Always maintain your expertise and visibly look for that as well. But again, the analyzer can prove to you that you have it. So what you have now is you have both a newer technician and an experienced technician that can prove and show to a homeowner or business owner, here is your crack in your heat exchanger, and these are the results of the analysis, and this is what it's showing you, and explain it to them. It ups everybody's game, and it increases everybody's credibility. And at the end of the day, what that increase in credibility does is it reduces liability significantly, because you've properly tested that appliance and have properly come up with what the numbers are and what the plan of action is going to be. Some different combustion results that we consider to be on the good side of the equation. We have a couple of different systems here. For an atmospheric system here, we look at an oxygen percentage of 7 to 9%, CO2 of 6.5 up to 8, and we have CO under 100 ppm. And that is a general guideline in our industry. The under 100 ppm in the stack is what you should always be striving for. Now, I know that you're going to say there are some manufacturers that allow you to have 200 ppm under high fire, 400 ppm on the stack under high fire. That's all well and good. But general industry guidelines are 100 ppm or less in the stack of CO under steady state running conditions. So always keep that in mind. When we look at your oil-fired systems, which is the crux of those of you at the Eastern Energy Expo, we have our 4 to 7% oxygen here, our 10 to 12.5% CO2, and we have our CO of under 50 ppm undiluted. And when we talk about oil systems, it's very, very important that before you perform a combustion analysis on a piece of equipment, on an oil-fired piece of equipment, that you do a smoke test. Because you don't want to put your probe into a sooted up or a very dirty system, because you have the ability or the propensity to pull some of that sootiness into the analyzer itself. And that will inhibit the analyzer's performance going forward and shorten its lifespan and also shorten the lifespan of your sensors. So it's very important that you perform a proper smoke test. Know that you have clean working conditions before you go ahead and start your combustion analysis. Typical good combustion results for a gas-fired system, that's the 3 to 6%. Again, CO under 100 ppm. But we've talked a lot about high efficiency or condensing systems. Your efficiency ratings here are 88 to 92%. It's actually higher nowadays. It's up to 98% now. But we have oxygen anywhere from 5 to 7, CO2 from 7 to 8.5, and CO again at under 100 ppm. Why combustion tests? Well, first and foremost, it's for the safety of the occupants and your own personal safety. We also want to measure the efficiency of the equipment and making sure that it is operating in the most efficient way possible and that we're not having any unsolicited losses and maintaining the proper operating conditions of the equipment. We also want to save money and having lower fuel bills, lower heating costs and the like. Very important when we talk about efficiency. We're going to have increased comfort, obviously, as a byproduct of that. And we want to make sure that we're complying with the governmental regulations. One of the other things we're testing, or why we're testing, is we want to make sure that we have proper fuel delivery going to that appliance. Towns and municipalities, or I shouldn't say towns and municipalities, fuel delivery companies, different gas companies, can have different amounts of gas pressure coming to spaces or coming to locations at different times of the day. So it's very, very important that we're actually monitoring gas pressure or evaluating gas pressure as part of our combustion analysis protocol when we're working on a system. We want to check the draft, obviously check the heat exchanger. All these different things are why we combustion test. Why do we need to measure? Well, as I said in the very beginning, the boiler and the furnace manufacturers are making it standard fare. They're making it a requirement now for you to qualify for warranty. Also, it's going to maintain the maximum efficiency for that appliance. And it's the way that the service professional should be doing his job and offering his service to the homeowner or to the business owner. It's going to help you comply with the federal, state, and local regulations when it comes to carbon monoxide, efficiency, and NOx. For the HVAC professional, you can use it as a sales tool, which I'll go over in a second. But it's also, again, the professional and correct way to conduct yourself on a service call. Anytime you touch a fuel-fired piece of equipment, you should be doing a combustion test so that you know what the baseline performance level is of that equipment. And also, when you use a combustion analyzer, it becomes, as you're going to see if you've never done it, and if you've already used one, it becomes an extremely valuable diagnostic tool for you as you move forward in your career and can help you diagnose issues with the system. The last one here is for energy auditing and weatherization groups. It's a required tool because you have to upload your combustion analysis in order for you to get your payment if you're a BPI contractor. So it's very important that you combustion test if you are in the BPI space. Energy auditing, BPI, like I just touched upon. Again, home energy assessments want you to do the combustion test. They want to make sure that we're not sealing up spaces so tight that we're producing excessive levels of carbon dioxide and producing high levels of moisture inside of a space because we're sealing them up too tight. And also, we want to make sure that we're having proper levels of CO in the different living quadrants in the house and also, or building, and also in the actual appliance itself. And again, this information needs to be uploaded for you to qualify for your payment, and it's part of your general operational protocol as a BPI contractor. How to make money with an analyzer. One of the things that a technician can do is to basically sell a simple 2-minute combustion test as a level of service, because chances are your competition is not doing it. You're going to alert a homeowner or business owner to potential problems with their system, but you're also going to justify if the piece of equipment is working at the efficiency level that they thought that they were paying for. And then you could possibly make adjustments to that system to bring them to within that efficiency level, whether it's different adjustments to the system, gas pressure, and the like. So again, if your customer sees you doing that, they're going to refer you to others, because customers will talk to one another. And if you're doing it and then the neighbor's contractor wasn't doing it, chances are you might get that business because you're adding an extra level of service and peace of mind that the other person was not getting from their contractor. Analyzer maintenance. Just a couple of things I like to touch upon here before we conclude for the day is, first of all, annual calibration. In a perfect world, a combustion analyzer should be sent in every year for annual calibration. Your calibration certificate is a legal binding document that shows that your combustion analyzer has been tested and evaluated for proper operating conditions for that year's time period that the combustion or that the calibration certificate covers. You always want to turn your analyzer on outside in fresh air with no probes or hoses attached. Very important, because you want to establish a proper baseline. If you don't do that, for example, and you turn it on inside, you might already have 100 ppm of carbon monoxide inside of a space, but you're not going to know it, because if you turn it on inside, it's still going to give you your 20.9% oxygen, your 0 CO2, and your 0 CO. So you might not know that there's already 100 ppm of CO inside that space if you turn it on inside. If you turn it on outside, like I have instructed you to do, as soon as you enter the space, you're going to see that 100 ppm show up right away in your display. You're going to know to shut the system down, open the windows, evacuate the occupants, and everything else that's going to follow suit after that. Cold truck storage. Analyzers and their sensors and anything else electronic really doesn't like extreme cold. So it is a strong recommendation that you treat this like a handheld computer, because that is what it is. You're not going to leave your laptop or your cell phone in your freezing cold truck overnight. Please don't do that with a combustion analyzer. Recommend that you take it in at night and then bring it back out in the morning when you're going to do your job for the day. Always check your water traps, depending on the type of product that you're using. Make sure there's no condensation or liquid in there. Make sure you empty that out before you test. And make sure you're also monitoring that amount of liquid while you're testing. That is very important as well. Because again, analyzers don't like water. Electronic equipment doesn't like water. That's why most analyzers have a proper water trap that can actually capture that condensation, that liquid, before it even makes its way into the analyzer and creating a problem. Make sure that you check your filters. You're checking your filter on your HVAC system in your home. Well, guess what? You have to look at and monitor your filter on your combustion analyzer as well. That is very, very important that you do that. A dirty filter creates a dirty operating condition for the analyzer. Us at Sauermann, we have a bunch of different videos that we have for you for training on the different products that we offer. I know I've went over today the finer points of combustion analysis and also some combustion troubleshooting. But again, we offer a vast array of instrumentation products that I went over in the beginning, and we offer an extensive amount of actual training. The training is not only on my end, but it's on the refrigeration instruments that I cover. We also have an industrial division that provides training, and we also have an IAQ division that provides training. And training is the wave of the future. Presentations like this are the wave of the future. So it is my hope that all of you that have viewed this have actually gotten something out of it and maybe came away a couple of steps smarter than before you sat down in front of your computer to view it. And with that, I would normally ask if I'm in front of you if anybody has any questions. However, as you see my little puppy here practicing her social distancing because we can't see each other in our presentations today. That's why we're doing it this way. But in any event, for those of you that have any questions, here is my contact information. My cell phone number is here. My email address is here as well. I will leave this up on the screen as I take a second to sign off. But on behalf of myself and on behalf of my company, the Sauermann Group, I would like to thank all of you at the Eastern Energy Expo 2020 for attending this presentation. Again, I hope that you garnered something out of this and hope that you will seek us out as Sauermann for your instrumentation needs as we go forward, and also seek us out for your training needs as we go forward. And again, my email and contact information is there. I wish you all the very best of luck. Again, I thank you for your attendance, and you take care. Thank you.